Hello all, welcome back to Code. Today let us solve the LeetCode's daily challenge. The problem is cheapest flights within K stops, and this problem is now graph problem because with this week we are actually following a pattern of graph in LeetCode's daily challenge platform. So there are n cities connected by some number of flights. You are given an array flights where flights of I is going to represent from I to I and price I. That indicates from the city from I to the city to I, the price is going to be the price I. That is what this flights of I represents. You are also given three integers, source, destination and K, and we want to return the cheapest price to reach from source to destination with at most K stops. So if there is no such route, we want to return -1. So this is the example 1, and let us analyze the example 1 to get a clear understanding. So in this example 1, the source is nothing but 0 and the destination is 3, and we have K stop to be 1. And when we create a graph using this flights array, it is going to be looking like this. And there are two paths from source to destination, which is 0 to 3. There are two paths from 0 to 3, 0 1 3 and 0 1 2 3. But you can see in 0 1 3, 0 1 3, there is only one stop at 1, and for 0 1 2 3 path there are two stops, but we cannot consider these two stops because we want to take at most K stops. In this example it is 1, so at most only one stop we can take, so that is why we cannot take this path even though it is giving the small cheapest price. That is, the cheapest price is 400 from 0 1 2 3, but there are two stops, so we are eliminating this path and we are going to this 0 1 3 path, which is having exactly one stop in between this path, and the total cheapest price will be 100 plus 600, that is going to be 700. So we want to find the cheapest price at most K stops. So hope you understand the problem now. So how can we solve this problem? So that we can actually apply in this graph problem, we can actually apply a Dijkstra algorithm. To a Dijkstra algorithm basically finds the minimum price from node source to destination using if the graph is having a weighted graph. If a graph is a weighted graph, so we can apply a Dijkstra algorithm. So Dijkstra algorithm is basically the priority queue that we will be using, and it is going to greedily say the node which is going to be processed next with the minimum price, so that by that priority queue we can basically find the destination with the cheapest price. If we reach the destination, when we reach the destination, it is going to be the minimum price that we processed till now. So that is how we can actually solve this problem using the Dijkstra algorithm using priority queue. So but do we want to consider any other cases? So let us have a priority queue, but what are the information that we are going to store in the priority queue? We want to store the city in our priority queue, and let us have it like this. We want to store the city, from which city we are actually coming, and then we also want to store the number of stops till now, because we should not exceed more than K stops, so we also need to keep track of that, and we also need to have the price from this city to the next city. We want to say what is the price till now, what is the minimum price till now. That is how we can push into the priority queue, and this is going to be the structure for the priority queue data type. And we can also create our custom custom class something with these member variables. But how it is going to be sorted, we are going to maintain a min heap priority queue where it is going to sort based on this price, and so that we can just greedily say which is the next city that we want to process. So that is how we can do. But basically in the Dijkstra algorithm we will be having a distance vector where that distance vector is going to say from X city we are reaching this Y city with this minimum distance, so that we can say if there is any other more distance coming. So let us say we are having a distance of 2 to be 2, distance of 3 to be 2, and if some other node we are some other path is having a distance of 3 to be 4, and we should not process that path as well, because that is going to give us a larger path. So we are actually redundantly calculating the distance. So what we can do is, similarly to the Dijkstra algorithm, standard Dijkstra algorithm, in this problem we are going to keep a array which is going to be named as stops, and this stops array is going to keep track of the minimum stops that we have reached from the node X till this node I. So that is how we can also eliminate the redundant process. So this is going to be acting as a visited vector if we are not going to visit the same path more than once. So that is how this stops array is going to be processed. I will just give a dry run with this first example so that you will get a understanding how this priority queue Dijkstra algorithm is going to work. So we are saying that we are going to push the city, stops and price. So initially the source is 0 and the stops is 0 and the destination and the price is 0. So this is going to be in our priority queue initially, and we are going to process this first node. From the source we are going to find the cheapest price till the destination we reach. So the next path from 0 is nothing but only 1, it can reach 1, and the number of stops will be incremented by 1, and the total price is going to be 0 plus 100, it is 100. And the next node that is going to be processed is nothing but this one. Only one node is there in the priority queue. We will just take it out and we will just process it now. And from 1 there are two paths, either 1 to 2 or 1 to 3. So if 1 to 2, then what will be the case? It can reach 2 with, we can say it can reach 3 first, and then it can reach 3 with the stops to be 2, and the total price here will be 700. As you can see that we want to have one lesser than k stops, or we want to have a condition which is going to be stops, which is going to be cut stops plus 1 is greater than or equal is lesser than or equals to k plus 1. We can have a case like this because the reached the node is also going to, we are going to increment as one stop, extra stop. So we can have a condition like cut stop plus 1 lesser than or equal to k plus 1. So this is the another node we can process, and the other path from 1 is nothing but 2. We can reach 2 and with stops 2, and the total price here is 200. Basically we are using a min heap, so obviously this node going to process next, and it will be inbuilt sorted like this based on this price. And the next node from 2 to 3 we can just go, and we can also go from 2 to 0, but as you can see the cut stop is nothing but 2 here, and we can have at most k plus 1 stops, which is 2, and we cannot go from 2 to 3 because it may go more than k plus 1 stops. We will go 3 stops, and it is not possible at all. So we will not push any other neighbor nodes that are directed from node 2. So what we can just do is we can just eliminate this now. Now we will just process this vector and this node. As you can see, we have reached the destination node. The total price we have reached this destination node 3 is nothing but 700. So that is how we are going to solve this problem. So what will be the time complexity for the solution? The time complexity for the solution will be there are v vertices, there are n nodes, we can say it as n. Obviously the graph we are going to have the time complexity as n plus e, and there are k stops, so we can say it as k. It will go till k. So till k times we can go have going on. There will be another loop, so that we can just say k. And inbuilt sorting in priority queue is nothing but it will be going to be log of e dot k, because there are e edges and k stops. So we can say it as log of e dot k, and this will be the time complexity for the solution. And what will be space complexity? The space complexity will be n plus e for the graph array into k, since will be storing in the priority queue e dot key elements, right? So that the space complexity will be n plus e dot k. So this will be the time and space complexity. So we can just now code the approach. You will just find it interesting since we will be using many classes and other data types which will be learning in this problem. So what we can just do is we can just first create a custom data type that is going to be the flight data. So we can say it as going to be the class flight data, and how it is going to be. So inside we want to say it as public, and it is going to be it is going to have city, then stops, then price. So these are the member variables inside the flight data. And what we can do is we can have first create a graph. What are the steps? We can just create a graphs initially. That is going to be a vector of int. It is going to be of inside it is going to be a weighted graph. So we also need the current to city and the price. So it is going to be the vector. So we want to push what is the city and the price. So what we can just do is we can have a pair of int comma int, and we are graph of size n. So we can also define the custom data type. I am just using a pair because we are just using to city and the price, right? So instead of that, so we can go for auto flight. In my flights, what we are doing graph, first we can get the from city. Int from is nothing but flight of 0, and the to city is going to be flight of 1, and the int price is going to be flight of 2, and graph of from the city we are going to city with this price. So graph of from dot pushback of 2 comma price. So we have just created a graph now. Now we also need to have a distance vector of size n. So we can have it to be the stops vector, the vector of int stops of size n, and initially it can be having a maximum integer maximum variable. And what else we need? We also need a priority queue of flight data, and it is going to be having a custom comparator. So we to have a custom comparator, the syntax is going to be looking like this, and this custom comparator we can define later. And this is going to be the priority queue, and this is going to be a min heap, and the min priority queue is going to be sorted based on the price. So initially we are going to push the source city, and then it is the source stop and the price. The price is 0 initially. So we have pushed the inside the priority queue, and we also can define the custom comparator now itself. So we can have it inside this class itself, inside this class solution. So what is the custom comparator? How can we declare? We can have a struct comparator and bool. So this is how we want to declare a custom comparator for a priority queue. It will be looking slight different from the sort custom comparator. So bool operator flight data ampersand a, flight data ampersand b. So these are the two things that can be done. And how we are going to do is price should be smaller. Price of a sorry it is basically the min heap. So for min heap, It is just opposite. If we need the smaller price should be coming to top, so we want to give as a greater than b. If we need a max heap, we will be giving a lesser than b. This is how the custom comparator for priority queue works. It actually be an opposite case. So return a dot price is greater than b dot price. So this will be having the smallest price at the top of the priority queue. So now we have just done it. So this is the min heap custom comparator, and what else we need? Now we can just do a Dijkstra algorithm, a standard thing. While not of priority queue is empty, while the priority queue is not empty, we can first get the current cut data. Cut data is nothing but the priority queue dot top, and we can pop it out also. And what is the from city? From is nothing but cut data dot city int stops, cut stops. We can say it as scarcity. Scarcity is going to be the cut data dot city. Cut stops is going to be the cut data dot stop, cut data dot stops, and int cut price is going to be the cut data dot price. So what will be our base case? If my cut city has reached the destination city, DST, destination city, sorry, we have just pushed the wrong. It is going to be the source node, then stops going to be 0, and the price is going to be 0. So yeah. Now the if my cut city has reached the destination city, then we can just return the cut price. That is going to be the minimum price that we have. And if else, if it is not, we want to have one case like the distance vector what we use in Dijkstra algorithm. We are having a stops vector. If my stops of if my curve stops if my curve stops is going to be greater than the stops of current city, then we can just continue because we have reached this path with the minimum price path already. We don't want to redundantly calculate. So curve stops is going to be greater than stops of curve city. Else we can just continue, or else we want to say the stops of curve city is going to be curve stops. And then what we can do is we can have a for loop that is going to go for all its neighbors, auto neighbors, or else we can have it as like this. It is going to be a pair, right? So we can have it as, I don't know, we can have the syntax, but let us try. If not, we'll just change it to that. This is going to be the two city. From this city we are going to this two city, and that is going to have this price, and it is going to come from graph of from. It is going to be Cursity, graph of Cursity. Hope you get my code understanding. So we are going for all its neighbors. While going for all its neighbors, we want to check the stops is plus. If the stops is greater than k plus 1, we cannot proceed further. We cannot push that into our priority queue. Else we can push. So we can say cut stops plus 1 is lesser than or equal to k plus 1. It is possible to push it into our priority queue. So priority queue dot push off. What at all we are going to push? We are going to push the city, stops, and the price. So cut stops, sorry, city is nothing but the city is the two city, and the stops is going to be cut stops plus 1. And what is the price? Price is going to be price plus the cut price, and this is going to be inside the priority queue. Yeah, we are done actually almost. So if I couldn't find anything, I will return -1. So we have done. Let us try to run our code. I don't think so any other thing we have to change. Let us run our code and see. I have missed something. I have missed a semicolon. Yeah. Great, it gets accepted. All the three test cases are getting passed. So I'll just give a quick skim into our code. We are having a custom comparator. We are defining, we are creating a graph. Then once we have created a graph, I'm having a step stops vector, priority queue, and we are pushing the source with the stops and the current price in a zero initially, and we are doing a Dijkstra algorithm. And basically while doing that, if we have found the destination, that is going to be the minimum price, cheapest price that we have to reach this destination, because of this priority queues, priority queues property, we are reaching it in minimum price. And if at all the stops is greater than the stops of current city, we are not proceeding further, else we will run into a infinite loop, and we are going for all its neighbors. And if it is having at most k plus 1 stops, we can definitely process that particular to city, and we are just pushing that into our priority queue and processing it. Now let us submit the code as well. Great, it gets accepted. Hope you like the solution, and the video seems to be too long, but hope you understand the problem. Let us see in tomorrow's LeetCode daily challenge. Until then, bye.